So what we have discussed was the stress distribution throughout the depth of the beam. Then we say distribution is going to be an elastic distribution since concrete beam did not crack yet. So as long as you're within the cracking limit of the concrete tension, this stress distribution should be fine. This is going to be the equation that we can use here, which is F equals to the moment divided by the moment of inertia. This is going to be the applied moment or the moment that you're going to be attaining. And then multiplied here by the y distance, which is the distance from the neutral axis to the point of interest. So interested in the stress at this level, this is going to be your y that you can use. So let's say interested in the stress at this level, which means this value here. How much is this? So in this case, I'm going to say the y value that I need to use is going to be from here to there. It's going to be your y value. If you like to get here to the maximum stress, which is this top of this triangle, you're going to be going all the way to this point. This distance from here to there, we call this C lowercase. So I'm going to use here C lowercase. Let's give you the distance here to use instead of using the term y. So this is going to be here C lowercase. Now, in this case, I can say that the stress on the top is going to be equal to the moment divided by the moment of inertia multiplied by C instead of y. This term here, moment of inertia divided by C, we can call this the section modulus, and we can use the term S for it. I guess we've gone through this slide already. We said that this is going to be for a general section, like a T section, not a specific case. Let's say, generally speaking, for a rectangular section, moment of inertia for rectangular section is going to be equal to BH cubed divided by 12. Section modulus is going to be equal to BH squared divided by 6. And I introduced this on the board last time. How do you get this section modulus? It's going to be like here, like using this equation. You just take this moment of inertia, and then you divide by y top or y bottom. Now, in the rectangular case, they're going to be equal to each other, which is equal to 1/2 of the height. So when you take this moment of inertia, divide by 1/2 of the height. You cancel this cubed, is going to be squared, and then 2 is giving the top. You cross it out, and then this 12 becomes 6. So it's going to be BH squared divided by 6 for rectangular section. When you have complex section, like this T section, you need to treat it in a special way. And we have a slide that was offered to you guys from previous class. How do you find out the centroid of the section? How do you find out moment of inertia for this? I'm going to say here combined section because you have two sections. The top is going to be the flange, the bottom one is going to be the web. And then you should be able to find out here the moment of inertia based on this equation. In this example here, we went through it quickly last time. We said given the section, you have some reinforcing bars that you don't really care about as long as you're discussing here the cracking point or cracking limit. Once you go here beyond the cracking limit, this rebars is going to be activated or triggered. And in this case, you're going to see some tension in this rebars. Before the cracking point, this rebars is going to be also seeing some tension. But the amount of tension that you're going to see, it is not going to be kind of significant. Like the analysis is going to show you maybe in this coming lecture. But the amount of tension that you have in the rebars is going to be very similar to any tension that you're getting concrete in this region. So it doesn't really make any difference whether you put rebars or you don't put them before the cracking point. Just by looking at this slide here, the only information that's going to be useful to me is going to be this 4,000 psi and this section information. Rebars is not really critical when it comes to pre-cracking. Now, how do you find out the cracking moment? By definition, cracking moment is going to be that moment at which the concrete is going to start to crack. And once the concrete is going to crack, if there's no reinforcing, you cannot really stop it. The beam is going to be failing. Concrete is going to crack at a stress of 7.5 square root of prime C. And this number here, it has to be in PSI. As I mentioned before, this code here is a PSI code. It is not kip and square inches or kip foot. No, it has to be all the equations. When you write it down in the code, it is all in PSI. So you do here FCR, this gonna be the tensile, cracking stresses, is gonna be 474.3 PSI. Based on this equation here, once the stress at the bottom of the beam, the tension side, is gonna be reaching this value, your beam is gonna crack. This is why MCR or M cracking is gonna be equal to the section modulus multiplied by FCR. Now you have FCR as a numerical value, and you have S also. You can figure out the numerical value for the section modulus, BT squared divided by 6 for rectangular section given in this example. And all what you need to do is just multiply the two values by each other. And as you see here, the difference between this value and that value is going to be converting it from pound inch to kip foot. How do you do this conversion? So let me write it here. So number one, you're going to divide by 12. You're going to put it in foot, and then divide by 1,000 to put it in kips instead of pounds. So from pound inch now is going to be kip foot, just by dividing by these two values for conversion. I said, okay. I said, okay, let me see here the homework that I assigned for you guys and how different it's going to be from this. Did you guys see the homework already? Here's the beam. Same beam size. 16 by 24. Okay. It says here, determine the modulus of rupture, FR, for the concrete. But this is here 5,000. This concrete was only 4,000. So I see here it's going to be just this equation, but you need to change the values. And then it says here, determine the section, moment of inertia, I, and the section modulus. Well, here it just showed here the section modulus. Now you know how to do the section modulus. But how about the moment of inertia? Do we have an equation for the moment of inertia? You can see, yeah, we have it. I'm just going to go back here. Here it is. This is the one that you can use for rectangular section. So you have a source for it. Okay. And then it says here, determine the cracking moment, MCR, based on the section modulus and the modulus of rupture. What's the modulus of rupture? This is going to be the 7.5. This item number 3 means that you're going to repeat exactly what we have done here in this example. Nothing new. It's going to be exact steps that we have done here. You need just to repeat it. All right. Why? Because this cracking moment, the one that I put here in the slide, is based on the section modulus, based on S, and based on FCR, which is, again, it mentioned here to be what? What does he call it here? The modulus of rupture, or the cracking point, if you like. So I don't want anyone to come here and say, what does mean by this modulus of rupture, right? We know it. It's going to be this FCR. So up to this item 3, everything is good. All right. I'm going to stop at item 3. I'm going to jump to problem 2 and then come back to 4 and 5. Why would I do that? Because now, by identifying the cracking moment, you should be able to solve this problem. It's going to be one full problem. At least you can do it and finish it. In this problem number 2, it says, go back to problem number 1 for this concrete beam cross section. The span and loading are shown in figure 2. Here we go. Here's the span, 30-foot span, 2-point loads, 10 kips and 10 kips. Let's give you right at the third point and the third point. And then it says here, draw the moment diagram ignoring the self weight of the beam. So self weight of the beam is not to be considered here. So what do you do? What is the moment it's going to be based on? It's going to be based off this 2-point loads. You guys know how to do it? Do you have any questions about it? Can you find out the reaction here? Yes? Can someone help me with this? How much is the reaction here and the reaction there? I see some people has their mouth open
10
as if they are
kips
speaking. Yeah, 10 kips, exactly.
on each side.
Yes, thank you very much. 10 kips, and in here also I'm gonna have here also 10 kips. Very good. How about the moment? How the moment is gonna look like? Is it gonna be above the datum or below the datum? What do I mean by that? Is it gonna be a positive moment or negative moment?
Positive?
This is correct. It's gonna be a positive moment because tension is gonna be at the bottom. So now for positive moment, do you want to draw it above the datum or below the datum?
Above.
Above, okay. So this is fine. No problem at all. Now, the moment here is gonna be equal to 0. And the moment on the other side is gonna be equal to 0. Since I have symmetry, I'm expecting here that the moment on this side is gonna be the same as the moment on that side. Let's take a section, cut a section right here at this place. Try to find out the moment. When you cut a section here, do you want to look right or do you want to look left? Which one is easier? Which one or which side that has less loads and less hassle? Let's say it seems that's gonna be the left side. Am I correct? Okay, let's look here. If you cover here, this side here, just cover it. I'm gonna say I'm gonna cover this piece here. Okay. Take the moment at this section to the left side. I have 10 kips multiplied by 10 feet. So I have moment of 100 kip foot. Okay. So the moment at this point, I can just put here a note for myself. Let's say moment here is gonna be 100 kip foot. How about in here, in this side, if I'd like to take a section right here? Now, which side do you want to look? Do you want to look to the right or to the left? Yes, say, certainly I'd like to look to the right. It's going to be easier. I have less loads to take care of. So I said, well, let me take the right side. I'm going to have here 10 kips multiplied by 10 feet. It's going to be also 100 kip foot. Okay, good. How about the moment in the middle? It's going to be straight line. The moment on the right side is going to be straight line between what? Between a 0 value and between 100. And here from 0 value to 100. And here from 100 to 100 is going to be straight line. So I'm expecting the diagram is going to look like this. How much is the maximum moment? Can someone just read it?
Is it 100 kip feet?
100 kip foot, exactly. This is going to be the maximum. Now, if this moment here, what do you call this moment here? Applied moment? Can I call it applied moment, right? This is going to be the actual moment based on the actual loading. It says here, check if the beam has cracked due to this given load. So when do you think this beam is going to crack? At what condition? Can someone help me with this? When do you think this beam is going to crack?
Once it goes over 100.
Well, do you know the cracking moment yet? Do you have the value for the cracking moment?
From part 1.
Yeah, so from problem number 1, first we need to know the cracking moment. Let's say the cracking moment is equal to 80 kip foot. All right. And this moment here is going to be equal to 100. So do you think that this beam has cracked or does still have some room before it cracks?
It's cracked.
It's cracked already because the applied moment is 100 and this beam can take up to 80, and right at that point it's going to start to crack. So if this moment is going to be higher than the cracking moment, it means this beam has cracked. If this moment 100 and let's say the cracking moment is 120, it means you still have a room before this beam cracks. Still some room. Meaning that this cracking moment, if you really want to understand it, it's going to be a limit. You can come, let's say, to this beam and put a mark there and say, cracking moment for this beam is going to be 80. If you don't want it to crack, don't put moment higher than 80 or equal to 80. Try to keep it lower than 80. If you don't care about the cracking, just go beyond 80 kFoot, which is going to be okay if this is going to be your design. So actually, this cracking moment is actually a limit. And sometimes we call it limit state. It is a limit or one of the section properties that you need to know. That this section here is going to crack at this given, let's say, moment the cracking moment. So I'm going to say, how about item 4 and 5? I'm going to say, you need to wait. I'm going to be working here some more, right? And do another example so that you guys understand what is the use of this forces that we're talking about. All right, so previously we said that I can take this force here and make it as, if I may go back here, 2 forces. We said that we're going to have here 2 forces. One is going to be compression coming this side, and here's going to be the tension force. And we said in order for you to find out this force, you need to do integration. What does it mean by integration? Integration is going to be the area under the curve. But when you have a surface, what does it mean by that? It's going to be the volume below the surface. So if you take this block and just move it out here, just to study it more in detail, I'm going to say here that this is going to be h/2, the height of this block, and the width is going to be equals to b, and the stress is going to be equal to this sigma c, which is in our case, I guess I said that we prefer to use the term F once we start work here with concrete, right? So it's going to be F, and usually we use lowercase. If you use uppercase, it means a force. If you use lowercase, it's going to be stress. Okay, this give you like the column. So how can I find this? I mean, how can you find out the force? This force C. I'm gonna say this force C, I guess I should be able to do it here. I'm gonna say C equals. It's gonna be this volume. How do you find out this volume? I'm gonna say it's gonna be equal to B times. Of course, it's gonna be times h/2. This time that, right? 1/2 of the height times this FC, so I may call this FC, if you guys don't mind. I'm gonna say times FC divide by 2. Why divide by 2? Because look at this triangular face. You can say this triangular face area is gonna be equal to FC multiplied by h/2 divided by 2, which means this term here is going to be equal to the face of this triangle. It's going to be this area here. Multiplied by the width of the beam, it's going to get you the force C, which is this one here. This is going to be the same. So this is going to be the force. Tension, of course, is going to be the same as compression. Otherwise, this beam is unstable. So I'm going to go back here to my homework to understand what does it mean by this force. Item number 4, it says determine the internal compressive and tensile forces in the concrete. Now I know what I'm talking about. This is going to be this C and tension. They're going to be equal to each other, and you can find it this way. So I guess in this example here, or in this homework, you were able to find out the stresses top and bottom. And how much is the stress is going to be? I'm going to say the stress at the cracking point is going to be equal to the cracking stress. So like in our example here, what was the cracking stress? Let's say cracking stress is going to be 474.3. In your example here, you're going to have, of course, another value, right? Because 7.5 square root of 5,000 is going to be different from this cracking stress. So what you need to do is to take this beam section, draw the stress distribution. So I'm going to say, okay, how can I draw it? Let's say, you know what? I need to draw this here, right? Now I'm going to come here and say, okay, here's the stress distribution. Let's give you something like this. It's gonna go like this, and this is gonna be like the data. Okay. How much is the stress in the top? I'm gonna say it's gonna be the same as FCR. It's gonna be the cracking stress, top and bottom. And then after this, you're gonna say, okay, here's the compression force, and here's the tension force. This is gonna be what? I'm gonna say this is gonna be C, and this is gonna be T. How do you find out C and T? You see, this is gonna be exact same thing that I've just done here, right? This is gonna be it. Just do this. You say C equals, and then you take the stress here on the top, which is the cracking stress, multiply by 1/2 of the beam depth, divide by 2, and then multiply by the beam width. Now it's going to get you the forces, and this is to solve for item 4. Now you have the tension compression force on the beam. If you recall, in the past I said, well, this distance here, you can call it JD, or sometimes you call it YCT, which means the distance Y from the tension to compression, Y sub CT. Okay. Which distance is this? Talking about this JD. It's going to be the same. How do you find it out? I remember that you guys helped me with it. I said, well, if the total depth is going to be 24 inch, like what we have here, and this is going to be at 1/3, this means this distance, the small distance from here is going to be 1/3 of half of the height. This is going to be 4 inches. And also from the bottom is going to be 4 inches. So we can say this also is going to be 4 inches. So how much is YCT in this case? YCT equals the total 24 inch. You subtract 4 on the top and 4 on the bottom is going to be 16 inch. So this is going to be YCT. Now, this moment that you're talking about, the same cracking moment, the same value, right? So we're going to go back to this slide set and say, where's the cracking moment? I'm going to say cracking moment, and say here, MCR equals to what? It's going to be equal to the tension compression. They're equal to each other, C or T, multiplied by YCT. Now, this compression force, it could be in pounds. Now you need to convert it, right? Put it in kips. And this distance here, you have it in inches. Maybe you'd like to divide by 12. Very similar to what I have done here, right? Exactly what I have done here, which means the first moment that you receive is going to be in pound inch. You need to convert it to kip foot, right? And this is here to solve the third or the last question asked. Determine the cracking moment based on the internal forces. What internal forces? I'm going to say this is going to be the internal forces, which means compression and tension. So 4 and 5 is going to be solved together. Your cracking moment here, out of this item number 5, it should be exactly the same as the cracking moment that you receive from item number 3. If it is different, you know that you have something wrong in your answers. It has to be exactly the same. Any questions? Any questions? Yes, no? Okay. So with that, you have kind of an idea how to do this homework, and it should be tough on you. So now let's move forward and look at the other example. We have this example 1-1. They give us here a beam, and the beam section is going to be 6 by 12. Let's say normal weight plain concrete, which means no reinforcing. So I don't know exactly what should I expect when it comes to the weight, but we're going to see in the solution. Could be maybe 150 pound per cubic foot, or maybe 145. Both of these two values can be accepted. Beam is simply supported on a span of 4 feet. So here's the span, and here's the beam. It has a point load, concentrated load, 4,500 pounds. The concrete strength, 3,000 psi. I know concrete strength is going to be important since I'm going to be doing the cracking moment. It says item number 8 says calculate the maximum concrete tensile stress using the internal couple method. What's the internal couple method again? This one you find out tension compression, which means first you find out the stresses. And once you find out the stresses, you should be able to find out these two forces. Is this the only way to use this internal couple method? You can say no. There's more than one way of doing it, but I'm going to say the easiest way to find out the forces is to find out the stresses, top and bottom. And then it says here, repeat part A using the flexural formula approach. I can show you what does mean by this flexural formula approach. And then item C says, compare the maximum concrete tensile stress with the value of the modulus rupture, FCR. Which means that you want to ask you, do you think that this beam is cracked or not cracked yet? Based on this loading given to you. Okay. Now, the self weight of the beam here needs to be included. In your homework, you don't really need to include it. So I need to find out the weight of the beam. The beam section is going to be 6 by 12. I need to put it as in square feet. And the reason because the weight of concrete is going to be 150 pounds per cubic foot. So this gives you the concrete weight, unit weight of concrete. 150 pounds per cubic foot, PCF. What is this 6 by 12? You see the section, cross-section area. You see this cross-section area, 6 by 12. Why divide by 144? Because I'd like to put it in feet. Because this value here is going to be given to me as in pound per cubic foot. So this cross-section area in inches, I need to put it in square feet. So we do the analysis and we come up with conclusion that the weight of this beam is 75 pounds per foot. So each foot of this beam throughout the length of it has a span of 4 feet, weighs 75 pounds per foot. Now let's look here at the moment, maximum moment that happened right in the middle. How can you find it? Well, I have two loads acting on the beam. I have the uniform load for the self weight, and I have a point load. I have here two loads. I have combined loading here. So I'm going to say, just for the point load, here's the maximum moment. So I'm going to say this is going to be for the point load. About the uniform load, I'm going to say uniform load is going to be this component. I'm going to put a box around it. So this term is going to be for the uniform load, W squared divided by 8. This is going to be the very famous one we know of. And this one is going to be for the point load PL over 4. The span is equal to 4 feet. And this is correct. Here's what we have. 4 feet here, 4 feet there, right? The point load is 4,500 pounds. Uniform load, 75 pounds per foot. Here's divided by 4 for the point load, divided by 8 for the uniform load. And here is the total moment acting on the beam right at the middle of it. So right at the middle span, your moment is going to be equal to 4650 foot-pound. Do you really want to keep it this way, or do you want to do it like as in kip foot? If you want to put in kip foot, just divide here by 1,000. So it's going to be 4.65 kip foot. So this is going to be the same as 4.65 kip foot. Okay. Now we're done with the demand. We did the uniform load, which means the weight of the beam, and we did also the point load. Combined effect of both of them is going to be 4.65 kip foot. Okay, total moment. Now I'm going to have here two forces, right? Tension, compression. And here's the stress distribution throughout the depth of the beam. Total depth of the beam is going to be 12 inches. So it's going to be from here to there. Neutral axis is going to be right in the mid height. Where is this point concentrated at? I'm gonna say this is gonna be considered at 1/3 of 6 inches, which means 2 inches. And this distance here is gonna be also this 2 inches. The distance between the tension to compression is gonna be equal to 12, subtracting 2 inches on the top, 2 inches on the bottom is gonna be 8 inches. This Z distance, you may also call it YCT if you want to. Y sub CT. Tension to compression distance. Okay, good. You know that this moment value, if you like, I can type here the equation for the moment value. I'm gonna say moment is gonna be equal to C or T times what? I'm gonna say times 10 inches, 8 inches. So okay. So if you want to find out this force, which goes with the applied moment, not goes with the cracking moment, right? Well, what you need to do, just take this moment, we just find out the 4.65, divide by 8 inches, and with that you find out this two forces, tension, compression. But this is not about cracking here. This is about the applied loads. We didn't mention anything about cracking. You see, in determination of this moment, this is going to be the applied moment on the beam. You may also call it load demand or moment demand. Okay, here's the equation for the moment. Moment is going to be equal to what? C times Z or T times Z, because T and C, they are the same. I said, okay, here's the moment value, 4.65. But be careful because this 8, which is a Z, is given inches. So maybe you'd like to multiply it just for units, right? You got to be consistent with units. So based on this, you say C is going to be equal to the moment divided by Z. And this is correct. We're able to get 6.975 kips. So I'm going to say here's C equals, let's say 6.98 kips. 2 digits should be fine. Should be good enough. This is going to be tension, also is going to be the same as the compression. So okay. How about the stresses? Can I find out the stress based on this? If I give you this force here, can you find out the stress? You can say, hold on. Let me go here back one step and show you the equation that we have used for this. In the past here, we said if the stress is going to be given to you and you want to find out the force, here's going to be the equation, the integration equation. And then in this case, you say compression force is going to be equal to the width applied by this little height, 1/2 of the depth, divided by 2, multiplied by the stress. Now, in my situation, in this example that I'm working on, compression force now is given to you. You have the width, you have the height, which is this edge. So the only unknown factor is going to be this F sub C, which means the stress. So finding out the stress, you can do it if you have the section modulus, you find out the moment, divide the moment by S, or you can do it this way, which is the internal coupled method. So this is going to be based on the internal forces that we are working with in this example. So I'm going to say now, let me move forward to my example. This is going to be here the moment, which is 4.65 kfoot. You divide this by 8 inches. Now you have the force. What do you do with the force? You do the integration equation. You say this compression force is going to be equal to 1/2 of the stress on the top, applied by 6 inches the width, applied by 6 inches, which is 1/2 of the depth. So let me confirm this equation here. I'd like to show you the picture or the diagram so that you guys are okay with it. So I'm going to say, okay, here's the picture. The stress is going to be in the top, right? The width is going to be 6 inches. 1/2 of the height is going to be 6 inches. So my equation, if you guys recall, the equation says C equals the width B times 1/2 of the height multiplied by FC divided by 2. So okay, let me take this equation here and remember that the width is going to be 6 inches, 1/2 of the height is going to be 6 inches. That's okay. Let me now move forward and look at it. It's right here. 6 inch for the width, 6 inch, 1/2 of the height times 1/2 times F on the top, And the whole thing here is going to be equal to 6.975, which is the compression force. So this is good. Now I should be able to find out the stress on the top. Here's the stress on the top, 388 psi, based on this equation. Okay. How about the stresses, top and bottom, based on the section modulus? Say based on section modulus. You can say yes. Like what we have done in the past with the very first example. You say, okay, let me find out the moment of inertia. Here's the moment of inertia, BH cubed divided by 12. Let me find out here the stress, top and bottom. Is going to be the moment divided by the moment of inertia, multiplied by C, 1/2 of the height. Here's the moment, divided by the moment of inertia, 864. We multiply here by 12, just because units, and then again multiply by 6 inches, which means 1/2 of the height. It turned to be the same, 388 psi. If you are getting here two different answers, something is wrong in your answers. You know that you have done a mistake, numerical mistake or something. Now the question is, this 388 psi is actually a stress applied to the beam. And the question is, do you think that this beam has cracked? I said, well, let's check here for FCR, which is this Modulus rupture. 7.5 square root of A prime C. This beam is going to crack at 411 psi. Therefore, this beam didn't crack yet because applied stress is lower than the cracking stress. So this beam is not cracking yet. Just to remind you here with your homework. In your homework, you're checking whether this beam is cracked or not, but you're not checking the stress versus stress. You're checking a moment versus a moment. The check that you're going to be doing, it is going to be applied moment versus cracking moment. Both methods are acceptable if you'd like to check if this beam is cracked or not. You can check a stress versus stress, or you can check a moment versus a moment. In this example, it was a stress versus another stress. The cracking stress versus applied stress. In your homework, it's going to be cracking moment versus applied moment. Any questions? Homework is easy? Great. I said, okay, I remember I have seen this before, right? That was a general T shape that we had here. Now let's give you that example with all numeric values. Let's give you example 1-3. They give you here, it says calculate the cracking moment, which is resistant moment. Let's give you the strength of the beam up to the cracking point. And they give me here F prime C, the concrete strength is going to be 4,000 psi. Assume positive moment, which means compression top, tension is going to be at the bottom, which means when the beam is going to crack, it's going to crack here from the bottom. So this is going to be the value that you need to set up equals to the cracking stress, not the top. See here, when you look at the T-shape beam section, and you study here the stress distribution, you find out here that the stress on the bottom is not the same as the stress on the top when it comes to value. I understand that this gives compression, this is tension, but because of the geometry, you find out the stress here on the bottom is going to be larger than that on the top. So this is why they need to be very specific and say this is going to be positive moment. When you have a rectangular section, it didn't matter because the stress top and bottom is going to be the same. So negative and positive moment, your beam performance is going to be the same. But for a T section, you need to be very specific. Where is the tension side is going to be? Because if this is going to be the tension side, we're going to set this value to be equal to the cracking stress. If they say negative moment, we would have set the top stress to be equal to the cracking stress. So here it says positive, this bottom is going to be equal to the cracking stress. It says here, use the internal couple method and check using the Flexural Formula. What's the Flexural Formula? The Flexural Formula means the stress is going to be equal to M divided by I times C, or M divided by S. This is called here the Flexural Formula. Internal couple method means that you're going to have tension compression, the distance, and then you figure out the moment based on that. You say moment is going to be equal to Z times C or T. Okay. Given information, they give me here the section 24, and this going to be 20, and this going to be 5 inches. And this is the way that you find out the centroid. You take the moment here about the top. You say A times Y for each one of these two sections. So what it means, you're going to divide this into two sections. Here's section number 1, and this give you section number 2. Cross-section area of section number 1 is going to be 20 times 4 is going to be 80, and section number 2 is going to be 100, 20 times 5. So yeah, I see this here, 4 times 20, 5 times 20. So this is actually is give you the cross-section area, right? And then you take this 22 inches, and this give you 10 inches for the distance from the reference datum. In a case like this, they decided here to do a datum right at the point, which is this reference axis. We quote here reference axis. The center of this first section is going to be at 10 inches from this here. And the center of the top section is going to be at 20 plus 2 is going to be 22 inches. And this is correct. Look at this, 22, 10 inches. And then you divide here by the total cross-section area. Total cross-section area is going to be 80 plus 100 is going to be 180. With that, you get here 15.33 from the top. Excuse me, from the bottom, from the reference axis. So this 15.33 is a distance from the reference axis, which means from the bottom. Okay. I guess this one also, this is what you call here y bottom. And the distance y top is going to be from here all the way to the top. It's going to be 4.67 plus 4 inches, going to be 867. Total of 24 inch. I say, great. Now I have the section properties. I have the cross-section area. I have the centroid location. And I guess I should start here to work on the cracking stress. Here's the cracking stress. And it's going to happen at the bottom because I have positive one. So this stress here at the bottom, I'm going to set it equals to 474 psi. This is going to be like code equation 7.5 square root of a prime c, right? So right at the cracking stress, this point for the stress here is going to be equal to 474. Can I find out the stress on the top in an easy way, just based on these properties? If I said here, this is going to be equal to 474 psi. How much is the stress on the top? Is there a simple way of doing it without going back to the moment equation? I'm going to say yes. There's a very simple way. If you take this stress 474, divide this by 15.33, it's going to give you the slope of this line. So from symmetry here, or because we have this two similar triangles, I'm going to say 474 divided by 15.33 is going to be equal to the stress on the top divided by 8.67 inches. Yeah, I said, okay. With that, I should be able to find out the stress on the top from this equation. So F top is going to be equal to, you find out, you just clean this equation, you find out the stress on the top. Here we go. Here it is. It's going to be 268 psi. So this going to be here equals, we can see here F top 268 psi. Very good. So now we have the stress top and bottom for this T section. Okay. How can I find out the forces? Can you find out the forces? Yeah, I said, okay, how can you divide the forces here? Tension is going to be simple because tension force is going to be equal to the stress on the bottom, the 474, times 15.33 divided by 2. Get here the area of this triangle, times the width 5 inches. But when you look here at the stress block over this T shape, where's the T shape? I'm talking about this flange and this little web up to here to the neutral axis only. You find it's not going to be that easy. And this is the reason I need to find out the stress at this point. Look, the stress right here. You zoom in. I'm gonna find out the stress right here at this location, meaning the stress here. I can do it to the same equation, but in this case, I need to know the distance from here to there. And how big is this distance? I have it, 4.67. So if you like to take this equation, let me just copy it here and let me see what changed. 474 divided by 1533 is going to be the same slope, but when it comes here, this is going to be 4.67. And it's not going to be F top, it's going to be F bottom of flange. So I'm going to say F BF, bottom of flange, which is right here, the stress right here. How much is the stress in this case? Can someone help? Yes? Yes?
Is it 144?
How much?
144.40.
144? Okay. Let's see what value we have here on the slide. Yeah, it's gonna be 144. Here it is. Exactly same equation we have used. Let's give 144 psi. Okay. That was easy. I was able to find out the stress here. Now let's find out the forces. And are we gonna have only one force on the top, one force on the bottom? Let me show you this. This illustration here shows you that it's gonna be really tough for the compression force to have it as one piece, because it is not gonna be a simple block that you can work with. It's gonna be kind of complex. So all of this, if you push this block here, this is gonna be number one. You push it, you put it against the section, and this is gonna be coming after it, and it's gonna be coming right below it. All of them, they're gonna be composing this triangular distribution. So if you look from the side, this is what you're gonna see. This section here, rectangular section, refers to compression force number one. And the width of this is going to be the same as the total width of the flange. The total width, right? Same thing for this little triangle. This is going to be C2. This goes also for the entire width of the flange. What is the flange? Someone's going to say, what is the flange? The flange is going to be this piece. The flange, this is going to be the flange. And what do you call this piece of the bottom? We call this the web. So you say this give me the web. The only force in the web, I'm going to call it to be C3, C1 and C2 is going to be the two forces acting on the flange. So here's C1, the entire width of the flange, C2 also the entire width of the flange, and Z3 goes with the web. So actually, when it comes to compression, I have these three forces because kind of complex shape. You have this T shape. Come to tension force is going to be simple. It's going to be this 1533 times the width times the stress divided by 2. So tension force is going to be simple. Compression force, now I'm going to have three compression forces. I need to divide the three pieces. Now, even before I'm able to figure out the value of each one of these forces, I should be able also to find out this Z distance from the tension force to each one of these compressive forces. For example, the first one is going to be at the mid height of the flange. So you say, okay, mid height compression of the flange. It's going to be right here. Yeah, this is C1. How much is this Z1? Well, first, where is this force? This 15.33 divided by 1/3. Okay, now I have this value here. Location of this T force is determined. How about location of C1? I know it's gonna be at 2 inches from the top. At this 2 inches. Yeah, I know it's gonna be right here. It's gonna be rectangular shape, not triangular shape. So you don't really divide by 3, just divide by 2. Now, how much is Z1? Z1 is gonna be equal to the total depth, 24 inch. Subtract 2 inches from the top. Subtract 15.33, divide by 3. With that, you get Z1. I'm gonna say, how about Z2? I'm gonna say, well, this little distance on the top is gonna be equal to 1/3 of 4 inches. Is right here. I said, okay, is this the one that you're looking at? Yes. And here is the point of application. How about Z2? Z2 is gonna be equal to 24 inches, subtracting 1/3 of 15.33, subtracting 4/3 of an inch. Okay, how about Z3? Well, where's this force is gonna be? It's gonna be at 1/3 of this little triangle. This little triangle, the height of it is 467. 1/3 of it is 467 divided by 3. Right? So the distance now is gonna be this distance from the bottom to this point, and then you subtract 1/3 of the 15.33, and then you subtract 1/3 of the 4.67. With that, you get these 3. So, okay, let me see this. Is this true? Is this what we have in this slide? I'm guessing, yeah, it's right here. And here's a good illustration to show you how it is calculated. Okay. So let's say, yes, now I'm able to find out Z1, Z2, and Z3. I'm gonna say, how about the compression force itself? Is there a way of finding out the compression force? I'm gonna say, yes. Here's a compression force. You have 3 compressive forces and you have the tension force, right? Don't forget, tension is gonna be equal to compression. So in this case, what tension are you talking about? I'm gonna say 1 tension force. How about which compression? I'm gonna say all the compression forces, they have to be equal to the tension force. I'm gonna say summation of the force in the x direction equal to 0. Yeah, at C1 to C2 to C3, they're gonna be equal to the tension force. Okay, let me see how the forces were determined. The first force is gonna be this rectangular block on the top. By doing integration to it, you can say, okay, this is gonna be the 144 psi times 20 for the width of the flange times 4 inches. So I'm gonna say, where is this 144 come from? I thought, based on this analysis, if you remember, it was equal to 268. I'm gonna say, you know what? This is 268, 144, 474. So let me go back here. The stress value that we're just talking about is gonna be equal to this. Correct? This value here was a 268 for the whole thing, 268 psi. And this value, which is right here at the bottom of the flange, you see this bottom of the flange? Let me zoom in. That was equal to 144. So if you want to find out C1, you take 4 inch for the depth times 144 for the stress, multiplied by 20 inch, which is the width. I'm gonna say, how about C2? C2 is gonna be this little triangle. It's gonna be equal to what? The stress. Which is stress? I'm gonna say the stress is gonna be from here to there. Let me put a line right next to it. This value is actually 268 minus 144. It's gonna be this little piece. Times 4 inch, multiplied by the width, the 20 inches. How about this here? This for the C3. You say, well, this here 144 times 467 divided by 1/2 times the width of the web, not the flange, because this is applied only on the web, which is 5 inches. Now let's see these forces. They're right here. Here's the third one that we were just talking about. Stress bottom of the flange times the width of the web times 467 divided by 2. So you have the 3 forces, and then you have the 3 distances, 3 Z's. Now, how do you find out the cracking moment in this case? You simply say, I'm going to be taking the moment about this point for all the forces acting in the system. You can say summation of moment at this section. So you're going to be looking at this and say, okay, this force is not going to be counted because you're going to be taking the moment about this one. So instead, you're going to have C1 times Z1 plus C2 times Z2 plus C3 times Z3. And this is going to be what? This is going to be the cracking moment. If you look here, next slide. Total resisting moment is going to be equal to MR1, which is C1, Z1, C2, Z2, C3, Z3. You just add them all to each other. That's it. So when you have a complex section like this is going to be the way to treat it. If you like to use the coupling method, which means put it as enforcers, it's going to be a little bit more work, right? But someone's going to say, how about finding it out with the Flexural Formula? Here's the Flexural Formula, which is right here. This is going to be the other method of doing it. You say, well, here's my understanding. So I'm going to write it here for you. You say the cracking moment is going to be equal to, let me put it differently. You say the cracking stress, this is going to be the easy way of doing it. It's going to be equal to the moment times Y bottom. Why bottom? Because it's going to be the cracking side. That's why I'm saying here Y bottom divided by the moment of inertia. Here it is. The cracking moment is going to be equal to FCR. Let me put this FCR is going to be in lowercase. The 474. This cracking moment is going to be FCR times the moment of inertia divided by Y bottom. So here it is. FCR times moment of inertia divided by Y bottom. Let me confirm one thing. Where is this Y bottom? How much was it? You guys remember? 1533, correct? Okay, yeah, it's correct, 1533. How about the cracking stress? Yeah, that was the 474 PSI at the bottom. I remember this value. I'm just going back to it. Let's give you the 474. So, okay. How about the moment of inertia? I said moment of inertia is going to be for this T section, this complex section. You need to study how to do this. We'll put some slides, and we have also here a very good example, detailed example shows you how to do it. So here's the moment of inertia. With that, you have the cracking moment. You see this cracking moment, if you use the Flexural Formula, it has to be exactly same value. Look at these two values. They cannot be different. I mean, you cannot have two different values unless you have done a mistake. Now questions. I'm done with today's lecture. I'm just looking forward for your questions.
Professor, the code on tests and quizzes.
Whenever you have a test or a quiz, I'm going to give you a formula sheet that goes with it.
Okay, so we won't have to bring like the book or anything for that.
No,
Okay,
I'll
thank
give you
you.
the needed equations, going to be within the quiz. And we're going to be doing it in class. So even if I didn't give it to you, I can put it in the projectors, give you on the slide. You can see.
Okay, thank you.
No. Any other questions?
Professor, recording anyone?
Yes, absolutely.
Oh, okay, making sure.
So I'll post it this evening.
Okay, thank you.
Yeah, no problem. Also, I'm going to give you a link. Canvas, you're going to see a link for lectures. It's going to be all the way at the bottom of the lectures.
Right, thank you.
No problem. More questions?